So we resume this afternoon session with Leonardo Cavenaghi to tell us about a new perspective on exhaustive manifolds, spherical duality, and Torus links. Leonardo.
Yeah, thank you very much. It's always a pleasure to be here. It has become a habit, so it's very
Habits are bad.
it's very good. Yeah, a nice place, and I'm thankful for the always welcome. Yeah, so I would like to continue Linus' first talk in the morning about this kind of duality that we have been visiting, but more from the point of view of differential topology instead of classical algebraic geometry and perhaps homological geometry instead. But nevertheless, it does appear some concepts related to that, and we are mostly focused on exotic manifolds. Right? For instance, exotic Hopf manifolds and this kind of objects. Just because, at least from my part, why do I get interested about this stuff is that because when you look to the curse of Riemann in geometry, there's no a single theorem that relates geometry, Riemann geometry, with a differential topology aspect, only with point set topology. And I always wonder why. One possible reason is that because when you put some Riemann matrix, you are at first assuming that you have an atlas already fixed background, but it's all interesting to know if there's something deeper going on in the analysis. So to begin with, just like it appears sometimes here, through this week, we have this classical vibration that's obtained out from the manifold that you can put here, CP1, and if you get like the projection onto the first factor here, and consider the Hopf map, then you obtain a vibration from this manifold here. That's usually called Hopf manifold, four-dimensional. And at least on my understanding, it grew of interest on this manifold because it was perhaps the first example of compact complex manifold that is not Keller for no compatible metric. So this is a complex manifold that doesn't care, doesn't admit Keller structure. So and this particular vibration here, A composed with phi from S3 times S1 to CP1, it consists of an example of elliptic vibration. Okay, and I would like to recall very quickly some structure properties of some elliptic vibrations. For instance, if you have like in general an elliptic vibration pi, then you have like some manifold here, either X that fibers over some manifold that if you want you can think that's always throughout this talk a CP1, then we can find some sigma 0 inside, sigma prime inside sigma such that it may happen that 4 points on sigma prime, the fiber here is singular. Nevertheless, we can, for instance, take this sigma minus sigma prime and denote it to be sigma 0, and then take the image, inverse image here that we shall denote by x0. Then we have like indeed a vibration, a classical vibration. That doesn't need not to be locally trivial, but a vibration. And some structure results that appears here is that, well, it could be not like a vibration that is locally trivial, but in some sense it can be taken from a principal bundle under fairly assumptions, meaning that we can find some principal bundle P0 over this sigma 0 with structure group being SL2Z such that our X0 is the associated bundle when you get the universal covering and then a representation of the fundamental group of the manifold on the SL2Z. So you do get a principal bundle. Oh, yeah, should not be this. You get a principal bundle that decouples that regular part of our elliptic fibration as a fiber bundle. This is true. So we have a sub-2Z. But why I'm telling about this kind of constructions in the sense of fiber bundles and this kind of stuff? Because it fits better to the context of the differential topology and the particular isometric group actions. So to elliptic fibration, we have associated this kind of structure results, and there is this work of Gomfi. Perhaps I'm mispronouncing his name. That goes back 91. It states the following. We have seen like yesterday and even today that for elliptic fibrations there is this procedure of named logarithmic transformation that can be used to convert some fibers into fibers with some multiplicity to your fibration, and it's a description from the point of view of GUI. Okay, and Gomfi, he did show that if you fix an elliptic fibration, or at least the regular part here, then there is some subset inside X0 there exists this that has the homotopy type S2, this mesh product with S2, okay, and such that its bounded is what's known as the three-dimensional Brieskorn sphere. So 6K minus 1, and oh, sorry, it's indeed some U here. Is this manifold here. We have, that's the Brieskorn sphere. Its bounded is the Brieskorn sphere that I will just recall to you. It can be written as the points U, V, and Z on C3, satisfying the equation. So we have this N, that's the nuclei, inside of the total space of our elliptic fibration. It has the homotopy type of the wedge product of two spheres, and it has as boundary the Brieskorn sphere. To classify what is the homotopy type of this Brieskorn sphere is only related to this Q and K. Okay, it can be, for instance, a quotient of SU2 by a discrete subgroup of finite order, or it can be indeed like a disk bundle over some surface. These are the only two possibilities. And more interesting, Gumpf also showed that this manifold here is such that to perform every logarithmic transformation coming from our initial elliptic fibration is only related to making the logarithmic transformation inside of this double tree. Inside the nuclei. You do not need to work on the whole manifold, on the whole total space of the elliptic fibration to do your logarithmic transformations. Moreover, if you have some, let's say, your manifold X, P1, Pk is obtained from your original elliptic fibration through K logarithmic transformations of multiplicity P1 to Pk, then and you want perhaps to determine the diffeomorphism type of this manifold in comparison to some other obtained different K logarithm transformation can indeed be some different amounts of logarithm transformation. It's solely related to understand the logarithm transformation made up in this nucleus. Meaning that if this you manage to get some diffeomorphism from here, then it extends to some diffeomorphism from here. So everything is encompassed on the nuclei. That has the property that this boundary is nothing but a Brieskorn sphere. Okay. So extends. And diffeom extends. And very particular in the to our most interesting example of a choice of P and Q over there to our Brieskorn manifold is associated naturally to 7-dimensional exotic spheres. To know let us consider this manifold here. That is the set of these points. Oh, I'm very sorry. I just realized that I forgot to mention that this is a continuation of Linus talk, but it's an ongoing work with Professor Leonardo Cavenaghi. I'm very sorry. Yeah, I should have mentioned this. Yeah, it is in the abstract. Okay. So, if we consider this manifold here, and then for this K, varying from 1 to 28, then this manifold, it parameterizes all possible homotopy types, all possible diffeomorphism types of homotopy 7-dimensional manifolds. Meaning that for each of these, we have that this manifold is homeomorphic to S7, the standard sphere, but not necessarily diffeomorphic. Okay, so we have this object here, but inside this object, we also have the Brieskorn sphere, because if we take the set of points U, V, Z0, then this is just the standard Brieskorn sphere with weights 6k minus 1 and 3. Okay, we have this, and just as we are looking in the context of elliptic fibrations, the manifolds over CP1, it would be with fibers T2, that is S1 cross S1. It's natural then to consider homotopy manifolds with some fiber here, and fiber possibly over some CP2. But what fiber to choose? This must be S3 and S1. So when you look to these classical elliptic fibrations, you usually have like a model as this homotopy Hopf manifold fibering over CP1. Here we are interested on this kind of fibration, where we have a homotopy Hopf manifold times S1 fibering over some CP2 with fiber S3 times S1. And just as introduced, we would like to understand what would be like logarithmic transformations in this scenario. And one thing that I can assure you is that suppose that we have a vibration like this, okay? Then our proposed logarithmic transformation is such that we do not need to perform it here. We only need to perform classical logarithmic transformations on the fiber. Okay? And different logarithmic transformations can yield different homotopy types over here. Okay? And this is a point. But what does this has to do with this T-duality and spherical duality that Lino was just mentioning? Before we come back to here and state what we can do from this stage, that is more or less the end of the story is to build some kind of homological inverse symmetry for these h-dimensional objects. What I must to present to you is that to our proposed constructions to make some different sensing of geometric constraints perceiving different smooth structures, we need to break somehow symmetry, meaning the following. Spherical duality, in the sense of booknet, everything in Matai, is equivalent, according to what we done so far, to cross diagrams. What are cross diagrams? For instance, an example that I can give you is that if we take this sp2 group, then we can put some S3 action that uses quotient S7, and this S3 action that is denoted by bullet on sp2 is 3. So this is a principal bundle. And you can cook up another commuting action by the same S3 that commutes with this action on bullet on sp2 and yields as quotient the Gromov-Meyer result here. Okay? So these two manifolds can be encompassed in a diagram where each of these is a principal one. Actions commute. So the star action descends to an action here. And this is 7. And the bullet action descends to an action here. And this is 7. Okay? And I claim that they find the same quotient that is an S4, but with output structure. Moreover, the orbits of the star action on S7 are the same up to some identification with the orbits of the bullet action on sigma 7. And these two constitute a spherical dual pair. And indeed, every spherical dual pair arises by the means of a diagram like this. Another claim that I make to you is that a diagram like this produces a Morita equivalence for the foliation generated by the orbits of the S3 action on S7 and for the foliation generated by the action of S3 on sigma 7. And this encompasses a Morita equivalence for the action group points. That happens to be equivalent to the spherical duality. But what does this give us to us? Well, if you take like S1 cross S1 here, and then cross S1, we can extend the actions so that we gain homotopy Hopf, but then we do not come to S4, but to CP2. And this still will be this kind of Morita equivalence for this manifold. But what does this mean to this context? It means that from the point of view of equivariant homology, this manifold has the same equivariant homology as this manifold. So if you look, for instance, for the chain 1 homology, from the point of view of orthofold on the function, it will not see exoticity. There's no chance of doing this. Even chain 1 homology does not distinguish the stacks coming from this homotopy Hopf manifold and this homotopy Hopf manifold. That's why we need to break symmetry to try to distinguish something. And moreover, indeed you can and find another precise information coming from this is that
Leonardo,
yes,
lost that you claim or you say that they are more equivalent.
yeah.
In what sense? In the sense of that something is a so in what sense?
You have foliation, right? You have the concept of Morita equivalence for singular foliations.
But they don't seem very singular to me. They look very
Yeah,
nice and.
No. The quotient here, the action that when you get to the action here, the action is not free on the quotient.
It is really more like a. You're saying it's more like a weighted projective space.
It is a weighted projective space.
That's what he's saying.
The quotient, the CP2 is a quotient, is a weighted projective space. It's not just standard CP2. Yeah, I should write this.
It's with a weight, okay?
Yeah, it's a weight. Yeah, there's a weight here. That's because it's not singular. It's singular. It's indeed singular. And the Morita equivalence here is from the point of view of because the S3 times S1 action here provides a foliation, meaning collecting the orbits of the group. Okay, and this is a singular foliation.
Because you're saying that the log transforms have singular fibers.
They do. They do. But I cannot distinguish them in the, when you're considering the full symmetry. Because the quotient built there is the same for the two manifolds constructed in the duality.
But one could just see it as that you have the top manifold and then you're quotienting one or the other or the one, and the end is the same stack.
It's the same stack. Yeah.
It's just a different way you're doing the quotient.
Yeah.
Okay.
Yeah. You that's exactly the feeling of this quotient. But the point is that this kind of construction is precisely spherical point. It is the same. You can build the flux and then construct the total space so that you are gonna collect everything to make the
This is
stack.
when there is no twist.
No.
Okay. But only because your quotient space is not a space anymore.
Exactly.
Would you be in a manifold, then there is no much
No.
going on.
Exactly.
You cannot do much.
Exactly. But yeah, the quotient usually is not a manifold indeed. It's a stack.
Exactly, but because it's a stack, then you're allowed to have a lot of twists that you can move around. Because if it were just CP2, then the multiple would be an isomorphism, perhaps, would be just the same thing. There's nothing else you can twist.
Yeah, exactly, precisely, yeah. And but from the point of view of the covariant homology, we cannot distinguish an option of the function.
No.
It's better, right? Even chain run homology. You know what I mean? Like that.
Yes, this is but this.
Yeah, because we do have like some HG from this S7 and this one.
But presumably the torsion in K theory or something like that.
Exactly, that's the point. That's
When these things are not, they don't detect this isomorphism invariant. They detect only homeomorphism invariant.
That's why we are.
Unless it's a complex.
No. But let me tell you why I think the torsion in K theory is okay. I can tell you why. Because we're saying, there's exotic structures, blah, blah, blah. But it's really a statement about a representation of a group.
Perfect, yeah.
It's really the thing is that in this case of the 7 sphere, the 28 differential structures is really just about certain characters of certain groups.
Yeah, Ernest is being precise. Yes, that's the point, because the exoticity is encoded on the action.
On the action.
Only.
So, of course, when you see the stack, you lost, but if you see the K theory, you see the representations back.
Precise.
That's the stack, you don't lose anything, it's everything.
Yeah, but if you do cohomology, but if you do the K theory or the Dirac category, then you should be able to see some sheaves and see the story.
Yeah, that's the main idea. Yeah, you just figure it out. Yeah, but this is the whole story. Yeah, because our construction theory, and that has to do with the breakup symmetries. And by the breakup symmetries, I mean like we have to choose carefully our actions to distinguish everything. Okay, because when you look here, then from the point of view of equivalent homology, you have the same thing for this example, for instance. And chain-one homology we coincide as well. And another relation with torical classical duality is that because this is also the torus. You take the maximal torus T inside here, this S3 times S1.
The whole thing is the non-abelianness of the group here.
Sorry.
Here the whole thing is that the main group in action is non-abelian.
Yeah.
So this is also
Yeah, yes. You mean that it's just determined by the torus, right? Yeah. It's just the torus here. Yeah. And then you take the fixed part by the U group associated to the maximum torus. So we can see nothing here. Even the chain run homology, when you look to the stacks, there's nothing to see here. That's why we need to come back to that description of manifold. And instead of look like to S3 times S1 actions, we look to SO3 times.
exactly. Now it's a non-abelian.
Exactly. And now you can see everything. Then you go to look for SO3 times SO2 actions on your parameterized homotopy of the manifolds. Okay? You are looking to this, and we can precisely describe what are these actions because we can see SO3 sitting inside O3, and then we can make O3 act as U3 on the coordinates. We have U, V, Z0, Z2, Z1, Z2 belonging to this pole. It's not sigma, it's that. We have this point here, and then we are going to see the SO3 action acting as U3 only on these three coordinates. Only on these three coordinates. So that we get like an orbit map for this action, just projecting into this UV. Okay, for the SO3 action on this manifold. And let's just circle multiplying trivially this SO2 if you want. You can make it complicated, but you don't need it right now. But then this projection here, when it has a very nice property, because we have then the following figure. We have SO3 times SO1 acting on this manifold that has a quotient, and now I claim to you that is this before that has an S3 as boundary containing singular orbits, and you have a torus link S1 consisting of fixed points. And then you can identify via this quotient map the quotient with the algebraic curve with this object here that is the singularity. That is the link for this algebraic singularity. Each homotopy Hopf manifold defines uniquely corresponds to a link of a singularity. Okay. So now we can see, for instance, try to extend homological mirror symmetry to this kind of manifolds just by looking to this kind of Brieskorn variety.
So it is going to delay the role with the model.
Exactly. That's precisely the point, yeah. This is going to be play the role of London Brieskorn model. So to the classical dual pair for homotopy Hopf manifolds, we associate some knot object here. and then that shall be playing the role of Leonardo model, and then we can just apply homological mirror symmetry to this univocally. Okay? This is more or less the main spirit of everything. Okay, it's more or less clear. So, because now we can just try to look to this thing from the point of view of singularity. For instance, we can compute the spectrum of singularities to distinguish these manifolds. You can compute the analogous to this Milnor algebra and what is the Milnor fiber and everything. You get some that's way more classic. This is just Torus knot theory. You have the genus, okay, you have everything, and then this is the analogous of your model. So in two ways, the point is that this J here can be obtained from also obtained from your Brieskorn three-dimensional manifold times S1. So every possible logarithmic transformation can be only made inside here. So the theory is natural, meaning that everything is encoded here. But to try to distinguish things, you have to put Abelian stuff here. Okay, so this is more or less some part of the history. And just to make some concise recap, then we are trying to understand homotopy Hopf manifolds, and we look at to S3 times S1 as fibers. This is not good because we cannot sense too much from the point of view of equivalent homology. Then we reduce symmetry to look into the SO3 actions on this S3 factor, and then we can distinguish quotient. And to each homotopy Hopf manifold, we can associate some algebraic curve that we can study from the point of view of singularity theory. And then it's just a matter of looking to this coordinate ring for this manifold and try to distinguish things. And that's what I'm doing on this very, perhaps 5 minutes only to make it shorter. So we have that curve that is associated to each possible homotopy Hopf manifold. And then we can take the ring of variables of your manifold, meaning that you take and you take the proj of your A. This converts your J in subvariety X on the weighted projective space of degree equals to 6 minus 2. Yeah, 6k minus 2, that's precisely the genus of the variety. The degree of your variety here is just the genus of your Torus knot. And then you get your manifold. And to this exotic manifold, we can associate we can take this group here, K, consisting of the points. So that it's possible to us to construct a morphism, homomorphism from this decay that maps alpha to alpha 6 chi minus 1. And we let G to be the co-pair of this map. And then G acts on the variety X. And then we get as they stack. And then we can do homological mirror symmetry for this stack. For instance, this polynomial here F, it defines a lattice vibration in the sense of serial. And then once it defines a lattice vibration, we can just look to the Foucault category of F. And one thing that you can prove is that the derived category of the Foucault of F, it coincides with the DB of this category. G, the genus. Of the graded algebras, or the bounded derived category of graded algebras, where G is the genus. So you more or less are on the step of obtaining homological mirror symmetry to homotopy Hopf manifolds in the edition 8, just by restricting the analysis that otherwise it was hard to curves on vertical spaces. It remains to prove that, well, because here we can consider the category of Euclidean sheaves. It's not true that it is in this manner isomorphic to the category of Foucault. We don't have this yet. It probably does not hold. It probably is false. It's probably going to be true only for the standard sphere. 7 times the standard 7 sphere crosses 1. But I don't know too much about this categorical stuff. I just know how to construct things, like this kind of examples. And related to this, this kind of work was initially thought to try to understand whether these exotic structures could be used or perhaps perceived from the point of view of differential geometry. So we ended up here doing categories. So this does not answer my question yet. And I don't think that perhaps this would ever be answered. Perhaps there's no way of perceiving like smooth structure from geometry. So in this sense, on the one hand, when you put to this Torus link stuff and you go on Google and type Torus knot generator, and then you plug the values of your Torus knot, you can perceive some difference. But what really distinguishes two smooth manifolds that have the same underlying topological space structure? That's something that it seems yet up to be determined. And I'm not sure, but when you look to this kind of homological mirror symmetry right on the beginnings, from these things getting the same physical meaning, perhaps it's just a question that geometry cannot be perceived somehow by any physical model or by any topological model. I'm being more precise here because geometry presumes a choice of smooth structure. So we always have to make some choice in advance. So perhaps this is one possible reason why we cannot perceive the different smooth structures, even looking to the homological side of the symmetry. But this is just a philosophical guess. And this is just a part of this story that we have been constructing with Vladimir and Lino. And there's much to come. For instance, how do ghosts enter all these kind of things? Because we have been considering the S1 action to be free on the S1 factor. But if we put some weight so that we produce some ZL as isotropy, and then things going to be way different. And it even lacks this kind of isomorphism. This does not hold anymore. So this is just the beginning of some history that I think that's enough for today. Thank you very much.